Okay, guys, thanks for being there. I'm Professor Abreu. Giuseppe is my name. I would like to today talk a little bit about not one, but several articles that we published recently, and I put them together into this presentation I call a discrete twist on the classical inversion problem. And here I'm playing a little bit with the spelling of the word discrete just to mention that there are in fact two different spellings of the word discrete. The first is this one, discrete, which means subtle, and discrete here, which is the mathematical case when things are non-continuous. So the talk is kind of a mixed match of a number of different contributions, but it focuses on a fundamental contribution, which is how can you solve the inversion, the classical inversion problem so prominent in communication problems and estimation theory problems and so on, in a particular case where the information you're seeking or the variables you're trying to solve for are discrete. Okay, so let's take a look at this classical inversion problem, very known to most people, or everybody, maybe who is working on communication and signal processing. You have a received signal Y or an observation vector, which here we are going to assume to be a complex vector of dimension n. So there are n different entries in Y. You have a information vector that is also assumed here to be complex, but of dimension n. And at this point, I leave it general whether m is larger than n or vice versa or equal. You have a channel or transformation matrix that maps S onto Y, except for the presence also of a noise vector, all of which again are assumed to be complex quantities. So now we're also going to assume, and this is under the classical scenario, that all you know about this problem is the received signal Y and the channel matrix H. So what you want to do at the end of the day is to estimate S, so obtain an S hat, such that if you multiply your known channel matrix H times the estimate of S hat, you get something that approaches Y as much as possible. So one way to define how H times S hat approaches Y is to minimize the least square or the square Euclidean distance between these two vectors. So this gives rise to this very basic formulation of the problem. We want to minimize, of course, over S, Y minus HS absolute square. Now, a classic solution of this problem is the so-called with zero forcing or least square solution, whereby all you do is, again, given the fact that H is not necessarily a square matrix, you multiply it by its transpose conjugate, and then you obtain a matrix that is a square, and then you can now multiply the whole result by the inverse of that product, leading to this expression here at the bottom of the slide. Okay, so this is known as the zero forcing solution, which, however cheap, easy, is also known to be not very good. Now, a slight improvement on top of that can be obtained if you assume that you also have some knowledge, some statistical knowledge of the noise that is affecting your problem. So in particular, if n has a variance n or sigma sub n square, then you can correct, so to say, the zero forcing estimator into what is known as the MMSE estimator, the minimum mean square error estimator, whereby essentially what you're doing is to sort of subtracting from the inversion solution, inversion-based solution that you're trying to compute, you are attenuating your confidence on your channel matrix, because you know that the channel is not the only thing that maps S onto Y. Also, N participates in that mapping. Okay, so you're trying to compensate, let's say, part of the knowledge is in H, but also part of the knowledge is in the statistical, yeah, the variance of the noise. All right, so now so again, the MMSE is known to be relatively good, better than the zero forcing, especially when noise is of significant value. Okay, it both reduce to the same when sigma n goes to zero, obviously. But this problem, both of these solutions are known to be very poor under the so-called overloading setting, in which the number of entries in S is larger than the number of entries in Y. Okay, so here's the situation when M, the number of entries in Y, is smaller than N, the number of entries in S, then this general matrix H is such that you can't even really do an inverse. You have to do a pseudo inverse that's shown before, and your problem is just essentially not fully determined, right? This is the classic situation. And it's true whenever your solution is to be found in the general set of complex numbers, as we started with. But there is more information that actually could be taken advantage of um, when you're solving this problem. One of them is, for example, the fact that you know S to have n different entries. Now, one recent, quite well-studied problem is the one in compressive sensing, when you say, actually, even if the number of entries n um, in S might be larger than M, if the number of non-zero entries in S is smaller than that. So in other words, if the norm zero of S is less than N and is equal or smaller than M, then the compressive sensing theory says, okay, you can solve this problem relatively easy, and there are many, many algorithms to do so. But I want to stress that here we are not talking about a compressive sensing case. We are actually talking about a case in which the zero norm of S is indeed N. In other words, there is no known zero entry in S. No or unknown. Yeah? So S is a full vector. Okay, it's not a dimensionality reducible vector, not sparse. Uh, so in that case, you would say, all right, then go home because there is no way to solve this problem. You don't have sufficient information in Y to solve it. That is not quite true, though, if you know S to belong, the entries of S to belong to a constellation of a finite number of possible values. So here represented by C, consisting of a number of complex values here, C1 to CQ. So in case C is a discrete constellation, in other words, S itself is a not sparse but discrete vector, then I put to you that as long as these possible outcomes are known, we can actually effectively, efficiently, and accurately solve this problem pretty nicely. So here's my problem statement. I want to know how I can reconstruct a truly overloaded, so not sparse, vector of discrete information signals. Okay, so you can go back to your classical formulation, the maximum likelihood formulation of the problem we briefly touched upon before, right? You'd like to minimize this distance y minus hs over s in the space of complex numbers, subject to now s not being only searched inside the solution space, but constrained to this domain of having only entries out of the alphabet. So, of course, if you try to solve this problem as is, you end up with an NP-hard problem because you'd have to verify all the time whether your possible solutions belong to the constellation or not. So this leads to a combinatorial problem. The only true maximum likelihood solution would be construct all possible interpoles of elements of C and check which one is best, which is obviously not something that is computationally efficient. So an alternative to doing that, though, is to say, let's compare each possible solution or each value of S against a vector constructed with only one of the entries of the constellation C at a time. So this is what I'm trying to represent here. So take as IC multiplied by a vector of all ones. So you have essentially S minus C1, S minus C1. So S1 minus C1, S2 minus C1, S3 minus C1, all the way to Sn minus C1 stacked up. And now if you look at the zero norm of this vector, what you are saying is you are essentially counting how many of these S's are not equal to C1, right? Every time the particular element in S is equal to that C1, then that difference is zero, and this drops the zero norm. Okay, so that zero norm, therefore, per vector, per I, is going to produce you a number less than n of outcomes of values that are not zero. So the zero norm is always smaller than n. And now you go, so it's essentially this number here, 2b minus 1. And you are going to do this for all possible constellations. Now here b is the 2 to the power of b is the constellation order, the cardinality of your constellation. Okay, so you now changed your constraints from being somewhat um, counting based constraint to be one that is normative, that is based on this norm. Problem is that this in itself is also not a convex problem because the zero norm itself is not a convex metric. So you are still not quite out of the woods, but you do have still in your hands the fact that now you have a finite number of C's to check through, given that Q itself is finite and the C's are all known. Okay, so again, as I said, because of the zero norm here, this problem is still in P hard. Now, what can you try to do? You can move this constraint to the objective by using a regularization coefficient, okay? And this leads to this, what is also known problem, known as the sum of complex sparse regularizers. So this problem was attacked here in this article from 2018 by Hayakawa and Hayashi. But what they did there was to essentially um, relax the zero norm into a one norm, and this gives you immediately a lasso kind of problem that you can go ahead and solve. However, I will highlight that in addition to that, you are kind of hiding the fact that you still would need to optimize the lambda, the regularization coefficient itself. So while the solution obtained by this work, is a step in the right direction, is not really what you want to do. Now, if you go and scavenge in the literature a little bit further, you will find that there are other solutions, and one interesting solution was this one where what is done essentially is to map everything to the real domain. So you split all your quantities, your y's, your s, your h, and n's into real corresponding equivalents, and then you can now formulate the real value version of the problem. And that problem, interestingly enough, was solved independently before by another Japanese colleague, Nagahara. Okay, so you can see clearly, and they baptized it the sum of absolute values. But again, at the end of the day, when you look at the fundamental optimization problem being solved by both of these works, they are actually solving exactly the same problem. The only difference being, of course, that when you're doing it into the real domain, you also have to map your constellation into the corresponding real parts. So you actually might sacrifice a little bit in the sense that if you have a non-regular complex constellation, when you map the real and imaginary parts, you might have a number P of real valued points in the constellation that is larger than the original number. But save these little differences, the problems are true. Both of problems are fundamentally the same. Now, what we are going to do, unlike those aforementioned works, is to actually stick to and kill the actual maximum likelihood problem posed as a regularization problem here, but without relaxing the zero norm constraint. We want to keep the zero norm constraint rather than relaxing it into an L1 constraint. That's one of the contributions. The other contribution is that we are also going to offer explicitly how you optimize this hyperparameter lambda. And finally, we are going to do all of this in a manner that can be solved in polynomial time. So it's the final algorithm we'll propose is something that is not an exhaustive search in any way. Now, without loss of generality, it should be clear that whether we address this issue as a real or complex valued alternatives or equivalents is completely the same thing. So without loss of generality, we are going hereafter to assume that all the quantities are real. But yeah, you could do the same arguments over complex case as well. All right, so the secret sauce, the first secret sauce of our approach is to take advantage of this interesting approximation, this smooth approximation of the L0 norm proposed in this article by Mohimani and Babayazadeh. So what they did was to say, all right, you can calculate the zero norm of a vector x by counting these ratios. So you take each entry of x squared and divide it by the same value again, plus some alpha of a relatively small value. So what happens here is that if x is exactly 0, you're going to have a 0 over alpha ratio, which is a 0. But if, on the other hand, x is a large number, then alpha is negligible in the presence of the large number, and then that ratio is 1. So you see why, for a sufficiently well-adjusted value of alpha, this is going to give you a very good approximation of the zero norm. Now, with a little bit of algebra, you can rewrite this ratio in this way, where you, instead of writing x absolute square divided by x absolute square plus alpha, you can write L minus alpha divided by x square plus alpha. And by doing that, you essentially eliminate one of the variables, which for the sake of optimization is meaningful. Again, please keep in mind that this alpha here is a parameter to be chosen really arbitrarily small, and we'll discuss this later. Okay, so these are just a recap of what we said, that if x is 0, then this is going to give you a 0, and if x is 1, then this is going to give you a value larger than 1. And here's a little plot of how that approximation looks like for different values of alpha, right? And so what you can see is that as alpha decreases, you have increasingly tighter, so we say this is an arbitrarily, asymptotically arbitrarily tight approximation of the L0 norm, because the function approaches the actual L0 norm for alpha going to 0. Now, the nice features about this approximation are, number one, this is a differentiable approximation. It's also continuous. It is asymptotically tight, as I already mentioned, but the one problem with it is that it's not convex. So let's, in any case, go ahead and employ that approximation into our previously formulated regularized problem. And I'm going here through the steps, right? So first, you just replace this zero norm of the match counting quantities here. Let's write it in terms of a sum. Now we can go ahead and baptize this result here as just the norm 0 of some x. Now you can go ahead and replace with the approximation. This is a constant that is now not relevant to the optimization problem. So we throw it away. We are down to this. And you immediately identify that this term here is a sum of concave over convex. So ratio function, right? You have a bunch of SCCR ratios, which are, of course, well known not to be convex in itself, but they are still differentiable, and they are continuous. And again, they are asymptotically tight because alpha can be chosen as it will. So here enter a very interesting contribution done by Shane in Wei Yu, I think known by many people by now, called fractional programming. And so essentially what is done here is that whenever you have a situation like that, where you have a concave function dividing a convex function, you can split this using a quadratic transform into a difference between the denominator, which is a concave function, and the denominator, which is a convex function, obtaining therefore a concave objective. Okay. Now the nice thing about it is that this is then iteratively optimized by computing a parameter beta, and this beta is given in closed form, taken directly from the SCCR ratios that you had above. So let's go ahead and apply this quadratic transform, or this fractional programming technique, onto the approximation of our L0 norm. So you can clearly identify that what you have here, in fact, is an affine function, and then you have here your concave. So if we apply the quadratic transform, you obtain the difference that we mentioned before, a quadratic function, and after some algebra, you realize that there are some terms that are independent of x. You can throw them away, and in the end, you're only left with something that is very easy to do, because it's just a quadratic on the variable x multiplied by this iteratively computed parameter beta here. Now, the beta itself is a function of x, but please notice that these x's here are computed based on the previous iterations, okay? So it is no longer a variable for the sake of the optimization problem itself. Okay, so here's now an example of how that um, convex-sized quadratic function-based or fractional programming-based convex-sized approximation of the L0 norm works out. Now, so here is a case where the approximation is using an alpha that is relatively large, and which is again a non-convex function, right? And then you are locally, for that iteration, approximating with this quadratic function, and essentially now as we go, we are going to decrease this value of alpha, making it tighter and tighter and tighter. And also you're gonna likewise shrink the girth of this parabola accordingly. Very good. So what is nice now is that thanks to the quadratic transform, you now have an actual approximation of the L0 norm that is differentiable, continuous, asymptotically tight, and convex. Cool. So if we put this now into our problem, we end up with this form. And now all is left to do is to organize things a little bit. Let's collect the values of betas and so on and so forth into this nice vector B and a matrix B, big B. We can now write everything in a matrix form as such. Yeah, we can now expand the quadratic term. Um, and then call all of these some function which is now fully convex, is just a quadratic function on S, which can be solved via conventional differentiation. So it's called the Wirtigan's gradient. You take the Wirtigan's gradient, equate it to zero, and you obtain a closed form. So watch out. This closed form here is a solution for a given iteration. So what we are saying, therefore, is that we can solve our original inversion problem via an iteration of these closed form expressions, in which case where the b's are being recomputed based on the previous solutions. All right. So in summary, look how in fact this resembles very much the zero forcing solution that we had before, right? Notice that in fact, if you make the matrix B and the vector B equal to zero, you go down directly to back directly to the zero forcing solution. Okay, so in a way, what we have discovered is that thanks to this quadratic transform, you can obtain a solution of the problem without relaxation of the zero norm via iterations of closed form expressions that resemble the zero norm. Very good. Yeah. So these here are adjusted adaptively. You can also understand with a little bit of inspection that this enforces essentially the fact that S hat belongs to the constellation. And these ones here also, this lambda B are diagonal updates of these um, square matrix that you have here, such that this can actually be the inversion that we have here can be done also quite efficiently. Now you don't have to always completely inverse. You can actually track the inverse by taking advantage of the fact that the updates are all diagonal. But I won't go into details of how you can do that. Okay, so far what we have done therefore is to obtain a so-called iterative discrete aware least square. We are using this term discrete aware in reference to the fact that your solution is already by default delivered in the form of something that is discrete. Okay, and it's iterative because again, like I said, it's obtained based on the iteration of this closed form expression. Yeah, and we obtain the solution with no relaxation of L0 into L1 via iterations of closed form solutions in an elegant and generalized version of the classic solver, the classic zero force solver, with very little added complexity because again, the inversions can be done with an updated with updates based on the diagonal additions. So these all comes as kind of bonuses beyond what I had originally promised to do. So let's take a look at some results. Here you see results in a loaded scenario, meaning that the number of transmit and the number of receive antennas are the same. So back to the notation I used in the beginning, my M and my N here are both 100. So it's a fully determined system. The dashed line is the solution you'd get with a conventional LMMSE. The black squares are the solutions that are obtained with the state of the art, either via that sum of what is that? The SOAV and the SCSR algorithms by the Japanese colleagues, and this here iterative discrete aware least squares is what we just proposed. And you can see quite clearly that um, and we have here results on the left-hand side with uncorrelated Rayleigh channel and on the right-hand side with correlated Rayleigh channel. We can see the correlation doesn't really disturb very much our solution. You can see, for example, that the gap resulting from correlation over the SOAV and SCSR is something in the order of, I don't know, maybe 2 dB. Yeah, something in that range. But for us here, it's just a fraction, okay, of dB. So it's really, really nice, very robust. Here again, solutions for the fully loaded case. But the more interesting case, yeah, we achieve a near optimality and low complexity, remarkable resilience to channel correlation. This is also much faster, so it's I don't know, not quite an order of magnitude, but about 5 times faster than the SOAV and the CSR. But even nicer, if you now consider the solution in overloaded scenarios, in this case where the number of variables is 120 and the number of observations is only 80, so you have about 50% overloading. Yes, you're going to have a performance degradation, but still we have a significantly nicer waterfall behavior compared to the LMFC, which is now completely saturated, and the SOAV and the STS. Yeah. Okay, so the achievements so far for the overload case are that in addition to everything else, we have no error floors, and we have some large gains over the LMMC and the SOT. Now the story gets even better. I am not going into more details, but these kind of gaps that you have here compared to the full maximum likelihood solution, the exhaustive search, can also be significantly improved if you just do coding. Okay, so if you use a little bit of redundancy and introduce some coding, you can get even better performances. But again, I will not go into more details. Rather, I want to address another issue that I promised before, which is how do we optimize this regularization term lambda here? So, in particular, I mean, and I might mention that in related literature, you very seldomly see anybody talking about how you optimize the regularizer, right? It's always assumed to be a parameter given by God, and you just hope for the best. But I'm going to show you right now in the next slide that you can actually obtain a closed form solution for that also. Okay, so we know that this is what we are solving at the end of the day. We started with this version of the problem, but we transform it into this convex problem here. And we know that the solutions are obtained by iterations of this closed form expression. Yeah, but we want to know, in order to be able to calculate this efficiently, you really want to know what the value of lambdas are. Now, the first inconvenience you have to deal with is the fact that you have to do this real operation here. That's kind of nasty to do. So in order to avoid that, we just throw in a bunch of algebra and move from complex to real. I think at the beginning of the talk, I said that I would say everything in terms of real, but I guess I misled you. Everything below was for complex values. And now if we go to the real case, then you don't need anymore to deal with that real. But again, as I explained before, that happens without loss of generality. So let's look at the problem, this variation of the problem in the real domain, where that operation of taking the real value is no longer needed. So now the other thing I want to do is to move my regularization term, this coefficient lambda, to appear multiplying the quadratic term rather than the other terms that came from the quadratic transform. And now some algebra taking place here, just expanding terms. I moved some of the terms back to a constraint, okay? And here I'm going um, to take advantage of this work here by Luzzi and Stelle and Link, where they showed essentially that this parameter here, that in principle should be a free parameter, should be also something you need to investigate, can be replaced by the noise variance. And now that I've done this, I take advantage of another work by José Morin that offers a way to solve such kind of problems. So this is essentially a quadratic constraint, quadratic program type 1 problem, and you can obtain the solution with basis on these two different equations here. I leave the details to for the reader to go to these papers. Now, again, a little bit of more algebra manipulation here and there. Realize that, interestingly, our regularizer now appears in the form of an optimized Lagrangian parameter that needs to be included. Then I take advantage again of yet another work done by Adachi and Akatsuka. And there, what we are trying to do is essentially to organize our quantities. I'm going to speed up things a little bit. There's a lot of algebra. You can read it in the paper. But after following all of these little steps, what is going to happen is that you start identifying a bunch of terms, all of which are fully determined either by the channel or the observation or quantities computed from them, like the B and the vector and the B matrix. So some cleaning up, some organization here and there. I'm going to speed up again. Bottom line is at the end of the day, you can write everything now in terms of a matrix problem. Yeah. All of these here are terms that I'll show them later again. And your solution that you are trying to obtain is extracted out of this vector here. So long story short, what we are talking about is fundamentally a generalized eigenvalue problem. So in other words, I'm saying that if you construct these matrices Q and P, check out the values, you can see that all of the entries here are extracted directly from knowledge, from things you know, the channel, the observation, and the iteratively computed matrix and vector big B and small b respectively. You solve a generalized eigenvalue problem, and that eigenvalue, the generalized eigenvalue, is in fact what you use to construct your solutions. Okay. So by comparison here, if I look at the solution obtained under this framework and what we had before, we can see that essentially the relationship between the maximum generalized eigenvalue and our regularization is just an inversion, right? So the optimal lambda is nothing but the inverse of the optimal generalized eigenvalue. And if you want to even save a little bit of time, you can even throw a Möbius transformation on the problem. So you just essentially invert the order of the P and the Q in your equation. And in that way, what you obtain is already the lambda that we are. Cool. Um, so this solution is very nice because if you are just finding a maximum eigenvalue, you can use the very stable power methods to obtain just the largest eigenvalue without having to do a full eigencomposition. So this is very computationally efficient. And because all the terms are power related, they are also very stable. It's very unlikely that you have things that are, ill-posed there. So here's a plot that shows the optimum regularized parameter for many, many realizations as the number of iterations grow. And another thing that you find empirically is that the variation is very small and that the value converges very quickly. You have one different value for the first iteration, but then for the other iterations, the values are pretty much the same. So this can be easily tabulated as well. So in other words, we obtain now a very fast converging solution over only a few number of iterations that is stable over many realizations. And as a bonus, we can now show, we have just shown you that you can find an algebraically optimized regularization parameter lambda instead of doing it via some, relying on God. I have here some results about what happens in terms of the convergence for different scenarios, fully loaded, overloaded, and so on and so forth. And you do find that correlation and loading have an impact on the convergence, but that's not of major concern. Okay, so let me summarize partially here what we have done. We have looked into the classic and the discrete version of the inversion problem, shown that we can obtain a solution in a very elegant form via iterations of something that resembles very much the zero-force classic solver, with a regularization parameter that is obtained also in closed form via the power method to solve the maximum generalized eigenvalue problem. And that's pretty much what we did so far. But there is more that we can do because we have at no point yet, except except mildly doing the formulation of the mechanism to solve lambda, we have not really taken advantage of knowledge of lambda of the noise. So, I mean, again, if we I mentioned earlier that the zero forcing solution is not that great in the presence of noise and is improved by the LMMSE, why shouldn't we try something similar for the discrete case as well? So this is one question that you should be asking yourself, and we asked ourselves as well. And that brings me to this next little part, which is about robustness. And I'll address not only the robustness with respect to noise, but also at the same time, I will address robustness with respect to other undesirable effects, such as channel correlation, estimation errors, and things like that. Channel estimation error in particular. Okay. So now what we want to do is go back to our problem, but keeping in mind an MSC perspective of it. You can now imagine that you are looking for an optimal combiner of the received signals that you apply before you do your search for your optimal result. Okay, so that's pretty classic. And you know that if you solve this, you're gonna find essentially that this optimal combiner is the MMC, right? Um, so applying that to our problem, what we're gonna do is to add to our objective a term that is also dependent on the noise power. And if we do that, uh, do some algebra here, using some linear algebra identities. Bottom line is that I fall into this problem here, which it should be recognized by you. It's almost the same we had before, except of the presence of this term here with sigma. Okay, so after all the steps of moving this as a regularization, relaxation, not relaxation, but approximation of the zero norm with the one norm, quadratic transform, etc., and splitting everything. Bottom line is I'm skipping the details. We land at this solution here. You can see how this is very similar to what we had before. The only difference, not surprising, is that this term appears in the inversion component or coefficient that you have to add here that carries the knowledge of. Everything else remains the same. Of course, the constructions of the P and Q matrix required to obtain the optimal lambda is also mildly adjusted due to the presence of the sigma square, but other than that, there is nothing really. So then, in other words, the incorporation of robustness to noise is very straightforward. Now, um, let's see now what happens here. So this is the sun. Okay, so if you assume that the noise is IID, Gaussian, etc., then all you need to do is to update our previous estimator by adding this term and of course reconstructing P and Q accordingly to obtain the optimal regularization term. So now the next robustness I want to address is what happens when these H channel matrices are not properly estimated. So in particular, we are going to make an assumption that these channels are actually the channel estimates H are only part of the true channel. So we use this very well-known standard Gauss-Markov model for the channel estimates. And this tau here is an uncertainty parameter that when set to 0 means that essentially you have perfect channel estimation. When set to 1 means that you have no estimation at all. This E here is a channel estimation error matrix. And in addition to that, we are going to model the channel estimates themselves as being correlated. So these guys here seem to be known, but they have some correlation covariances that are part of their construction. In addition to all of these, I'll also throw in one more complication, which is what happens if you have transmit distortion. So if you're trying to transmit S, but you for whatever reason you transmit a noisy version of S due to, I don't know, some effect of your power amplifier or whatnot, or let's say that you operate in a full duplex system, so you have S plus omega instead of just S. Then you have this transmit distortion as well. If you add the transmission distortion, this again will appear in your received signal in the form of these CSI imperfection and hardware impairment components that are highlighted in the bottom of the slide. So what we do essentially is after everything is taken into account, treat all of these nuisance terms here into some equivalent noise And once you do that, you can also obtain a corresponding covariance matrix. I'm rushing a little bit here because the key thing is really to see the final solution. So there's a lot of algebra. I leave you to do it, to check out in the paper. But anyway, we take that covariance matrix and we split into some central part and some non-central parts. So we split it into two components, right? The sigma C and the sigma U. And then the problem is that if we just continue as we are, we would violate the Woodbury lemma. So in order to avoid that, we move from the original Euclidean distance between y and h times s that we had before for Mahalanobis distance, where um, this I think this is a non-central this correlated noise. So this is due to noise correlation. So this correlated noise component is used to modify our quadratic term in the objective, and the rest is pretty much the same. So long story short, again, look at what we get. We land at a solution that once again resembles very much the MMSE. Only this time you have a correction term that takes into account not only the power of the noise, but also the uncertainty coefficient due to imperfect channel estimation, and where your construction of your rectangular matrix to do your pseudo inverse also is based not on an Euclidean distance concept, but on a Mahalanobis distance. Okay, so you can see here how this fully generalizes what we had before. If you make sigma equal to zero, you go back to the any tau equal to zero, you go back to the MMSC. But if you don't make tau zero, you have an MMSC with imperfect channel estimation. So there's like a bunch of buttons. You can push all the buttons you want. The derivations of the matrices P and Q are the same as we did before. Their constructions are slightly different, of course, depending on all, they are now since they are now depending on all the other terms, but you can find the details in the paper. I show you here just quickly how they are modified respectively. Okay, so here I show you some results with loaded and correlated with channel state information errors and with hardware imperfection. And what you find here is that and I'm showing this here as a function of the channel uncertainty coefficient as well as some correlation coefficient. And you see that again, the proposed method outperforms everything that we can think of and that we know about to date. And yeah, so here is the case for a fixed value of correlation, and here's the case for a fixed value of channel uncertainty. Those for uh, These were for a fully loaded scenario and here for an overloaded scenario. Once again, we see that we outperform everything else. Let me summarize what we have done. So we have found a very, very powerful, general, and elegant solution for the discrete inversion problem, taking into account a large number of issues, including the fact that the transmit vector, the system might be overloaded, might be affected by transmit uh, imperfections. It's affected by noise. It's affected by channel estimation errors, and all of that. Okay, channel correlation and all of that. Okay, and the solution is given once again in the form of a simple iteration of these closed form expressions with these lambdas determined optimally and algebraically via a generalized maximum eigenvalue problem. Let me see if I have anything. Yeah, I'm just highlighting here that these terms here account for the discreteness. This term here accounts for the resilience against CSI error. This term here accounts for the resilience against noise. This one against the resilience of correlation and hardware imperfection. And once again, you can see how this resembles a zero forcing or an MMSE solver, with the only difference that these expressions here are computed iteratively as opposed to a single shot as they would be in the zero forcing and the MMSE cases, respectively. Now I'm going to just highlight that all of this work you can find in this article here, published in the Open Journal of Communication Society, titled Robust Signal Detection in Overload Normal Systems. But I'll also point out that we have a conference version preceding that journal, with the title An Iterative Discrete Least Square Estimator for Dynamic Parameterization over Unfolding. And in that paper, we actually also addressed another interesting case, which is, can we obtain this parameterization regularization term lambda via machine learning? And the answer was that yes, we can do that. I have also a number of problems that I could talk about, including matrix that relate to this, including matrix completion, um, including let me see, I have matrix completion, I have um, inversion, joint inversion and estimation. So when you have a two linear problems to be solved simultaneously, um, and when you are trying to design optimal frames for multiple access, and finally, when you are trying to do tensor decomposition, on all of those cases, these concepts that we put here can be utilized, but I won't go into more detail. Thanks for the attention. And in the description of the video, I will also put links to all the articles that we mentioned. Thank you very much, colleagues, if you have any questions.